Good morning, everyone. In today's lecture, we will discuss about the p-block elements, the main characteristics of the p-block element. In ongoing lectures, we are just discussing about the characteristic of S-block, p-block, d-block, and the f-block elements. After that, we will see in detail about all the properties one by one of these all S, P, D, and the f-block elements. So in today's session, we will just give a brief review about the p-block element characteristics. So let's start our today's session on the p-block elements. What are the p-block elements? The first property will be the definition of the p-block element. So what are the p-block elements? The p-block elements are those elements in which the last electron enters into the valence p subshell are called as the p-block element. So here is the configuration of the boron, atomic number 5. Configuration is 1s2, 2s2, 2p1. You can see in that particular diagram here. In the center, there is a nucleus, the first shell. In first shell, there are the 2 electrons, that is the 1s2. In the second shell, there are 2 subshell, 2s and the 2p. In the 2s, there are 2 electrons, 2s2. In the 2p, there are the 3 orbitals in the p subshell. So there is 1 electron. Means one of the electron can jump into the 2p. 2s electron can be jump into the 2p. So there can be a maximum of 3 unpaired electron after the jumping of that. Why the 2s electron can jump into the 2p? Because of very less energy gap between the 2s and the 2p subshell. 2s and 2p subshell has very less energy gap, and due to very less energy gap, the 2s electron can be jump into the 2p, and thus it can increase their valency. It can increase their valency. It can expand their valency due to the presence of these vacant 2p orbitals. If these vacant 2p orbital are not present, then these 2 electron, these 2s electron will remain in paired state. तो वे paired state में रहेंगे. But as there are vacant 2p orbitals, so that 2s electron can easily be jump into the 2p. So the maximum number of unpaired electron in the boron will be 3. So due to the presence of these 3 electron in their valence shell, the boron can form 3 bond. Means the valency of the boron is 3. So these group 13 elements, maximum valency is 13. Element is 3. You can see in all group elements in the p-block element group 13 to group number 18, because the p-block element ranges from group number 13 to group number 18. Why there are 6 group? Because in the p subshell you can see there are 3 orbitals, 1, 2 and 3 orbitals, and there can be a maximum of 6 electron, 2 electron in one orbital, 2 in another, 2 in another, total 6 electron can be placed in the p subshell. So there can be a maximum of 6 group. So there are 6 group for these p block elements, which ranges from group number 13 to group number 18. And in from group number 13 to 18, there is one interesting thing. In group number 13, the last numeral value is 3. So their maximum valency is 3. Maximum valency of any of the element is 3. In group number 14, the last numeral is 14, 4. So maximum valency is 4, and so on. Ranges from group number 13 to 18, except the group number 18, which has the fulfilled stable configuration. They have no tendency to form any type of bond, means they are less reactive, they are inert in nature, they are noble gases. Now you can see all the 18 vertical columns, means these are the 18 groups in the periodic table. You can see here the 7 horizontal rows. These are the periods. Now we will discuss here only about the p-block element that ranges from group number 13 to group number 18. So in group number 13, the elements are boron, aluminium, gallium, indium, and the thallium. That boron, that comes in the second period. That is a second period element. Aluminium, that is the third period element. Gallium, that is the fourth period element. Indium, that is the fifth period element. The thallium, that is the sixth period element. As the boron is the second period element, and in the second shell, in the second period, you can see there can be a maximum of only 2 shell, first shell and the second shell. In the second shell, there is only S, and the P there is no D, means the second period element has no vacant D orbital. They have no vacant D orbital in the second paired element, whether these second paired element are of group 1 or the group 2, that is of S block element, or these element are of P block, whatever may be the nature of the element, whether they are the S block or the P block, all the second paired element has no vacant d orbitals. That is very important fact which will be used later on in the different type of reasoning questions. In the group number 14, the first element that is of second paired element, that is a carbon. The next after carbon, that is silicon, that is the third paired element. Next one is germanium, that is a fourth paired element. Tin, fifth paired element. Lead, that is the sixth paired element. These are the group number 14 elements. In group number 15, nitrogen, phosphorus, arsenic, antimony, and the bismuth in the similar way. Group number 16, oxygen, selenium, tellurium, polonium. These are the group 16 element. Group 17, fluorine, chlorine, bromine, iodine, and the astatine. In group number 18, helium, that is the first paired element, helium, neon, argon, krypton, xenon, and the radon. So these all are the p block element, which ranges from group number 13 to group number 18. The next important feature of the p block element means about their electronic configuration. What is the general electronic configuration? When we write configuration of all the element, then and only then we can understood about the general electronic configuration, means the element which is common for all the p block elements, that is the general electronic configuration. The general electronic configuration of the p block element is ns2 np1 to 6 except helium, because in case of the helium, the configuration is 1s2. There is no role of the p here. You can see in the diagram also, nucleus, the first shell, which has only 2 electron in the s subshell. So exception here is the exception to that general configuration of the p block element is helium. That is the helium that you have to learn for the examination point of view. Helium has only 2 paired electrons. That helium has fulfilled configuration. These electrons cannot be unpaired. The helium cannot form any bond. Helium cannot exist in the form of He2. That can also be explained on the basis of molecular orbital theory also. And you can see also here, okay, these 2 electrons cannot be unpaired due to the absence of any of the vacant orbital in the helium. So helium cannot form any bond. Next, you can see the next element, that is the group number 13 element, that is the boron here. The configuration is 1s2, 2s2, and 2p1. You can see it by the diagram also. In the center, there is the nucleus. Then there is a first shell. In the first shell, there are 2 electrons, that is 1s2. In the second shell, there are 2 subshell. In 2s, there are 2 electrons, 2s2, and 1 electron in the p, that is the 2p1. As we already discussed, that one of the 2s electron can be jump into the 2p to increase their valency, to expand their valency. So the boron can form the 3 bond due to the presence of 3 electron after jumping of the 2s electron into the 2p. Next one is the carbon. The configuration of the carbon is 1s2, 2s2, 2p. 2, you can see, as we are moving from left to right in the periodic table, means from boron to carbon, what you have seen here, the number of shell remains same. You can see in boron, there are only 2 shell, first shell and the second shell. You can see in the carbon also, there are only 2 shell, first shell, that is 1s2, you can see here. Our configuration of carbon is 1s2, 2s2, 2p2 in 2s2 and 2p2, one more electron in the 2p as compared to in case of the boron, because atomic number of boron is 5 and the atomic number of carbon is 6. So one more electron, that one more electron enters into the 2p. Now also there is the one vacant orbital in 2p. So that 2s electron can be, one of the 2s electron can be jump into the 2p. Because of the less energy gap in between the 2s and the 2p. So one of the 2s electron will easily be jump into the 2p. So the valency of the carbon will increase up to the 4. Maximum increase up to the 4, means carbon can form 4 bonds. Now the next element on moving from left to right in the periodic table after carbon is, that is the nitrogen, whose configuration is 1s2, 2s2, 2p3. But one common thing that we are seeing here on moving left to right in the same period, that is in the second period, the number of shell remains the same. The number of shell remains the 2, because these are the second period element. Second period means they have only 2 shell, and all element have the 2 shell. Boron 2 shell, carbon 2 shell. Now the nitrogen, that only 2 shell. You can see in that diagram also here the configuration is 1s2, 2s2 and 2p3. Now there is 1 electron each in each of the orbital of the p subshell. In the 2p subshell, in each of the orbital has 1 electron, means using the Hund's rule, which states that among the degenerate orbital, these 3 orbitals of the p have the same energy, and these same energy orbitals of the same subshell are called as the degenerate orbitals. So among these degenerate orbital, there is 1 electron each. And why these 1 electron each? According to the Hund's rule, which states that among the degenerate orbitals of the p or the d or the f subshell, the electrons are first of all filled up singly, then the pairing will start. So here electrons are filled up singly, one by one, in each of the orbital. So now there is no possibility of jumping of that 2s electron into the next one, because there is no possibility, because there is no vacant orbital, because in the second shell there is no 2d, so there is no possibility. So these 2s electron remain in the paired state. The 2s electron of the nitrogen remain in the paired state, and there is only 3 unpaired electron in case of nitrogen. So nitrogen valency is 3. Nitrogen can form only 3 covalent bond, but due to the presence of that 1 lone pair, the nitrogen can form 1 coordinate bond, 1 dative bond. So the maximum valency for the nitrogen is 4. 3 due to the presence of these 3 unpaired electron, due to which the nitrogen can form 3 covalent bond, and due to the presence of that 1 lone pair, it can form 1 coordinate bond if there is such type of requirement. So that about the nitrogen. Next element on moving from left to right after the nitrogen is oxygen. In oxygen also there are 2 shells. The diagram here is 1s2, there are 2 electron in 1s, 2s2, 2 electron in 2s, and 2p4 means, according to Hund's rule, as we already stated, that among the degenerate orbitals of the p, d or the f subshell, here the p subshell, the electrons are first of all filled up singly, means 1, 2, 3, and then pairing will start. Then the 4th electron comes here. So Hund's rule is applied here. So according to the Hund's rule, the configuration can be shown like that in the diagram also. After oxygen, the next element is the fluorine. The number of shell will remain also same. That is the 2 shell. The configuration is 1s2, 2s2, 2p5 here. So means these 5 electron, according to the same Hund's rule, electrons are first of all filled up singly, then pairing will start in the degenerate p subshell. So 1, 2, 3, followed by electron, the pairing, the 4th electron, then the 5th electron. Now, in case of like that of the nitrogen, in case of oxygen and fluorine also, these 2 electrons cannot be jumped in the outer orbitals, because there is no scope, because there is no vacant orbital in the oxygen and the fluorine also. So the unpaired electron, in case of oxygen, there are only 2 unpaired electrons, so it can form only 2 covalent bond. In case of fluorine, there is only 1 unpaired electron, it can form only 1 bond, 1 covalent bond, and the remaining electron are the lone pairs. So you have to learn all these things. Means in case of the nitrogen, you can see in the diagram, nitrogen has 1 lone pair and 3 unpaired electron. In case of the oxygen, there are the 2 unpaired electron and 2 lone pair electrons. Means we are talking about the valence shell electrons. What is the arrangement of these valence shell electrons? How they are present in paired or the unpaired state? On that basis, we are talking about these bond pair or the lone pair. So in oxygen, there are the 2 bond pair electrons, 2 lone pair electrons. And in case of the fluorine, you can see these are the 3 lone pair and the 1 bond pair. And in case of neon, the next element is neon. On moving left to right in the second pair, the next element is neon. In the neon, all electrons are present in the paired state. All are the lone pair. There are the 4 lone pair. The configuration of the neon is atomic number 10, 1s2, 2s2, 2p6, 2s2 here, and 2p6. So the fulfilled configuration of the neon, fulfilled stable configuration, and there is no scope of being unpaired. We can't unpair these paired electron due to the absence of any type of vacant orbital. There is no vacant d orbital in the second shell. There is no d possibility of d. There is no d, so no d orbital, no vacant d orbital. So the neon cannot form any bond. So that is the about the next point, that is about the general electron configuration. Now you can easily been observe, in case of boron there is one unpaired electron. In case of P there is one electron. Next carbon there are two electron in P. In case of nitrogen 3 electron. Then there are 4 electron in case of oxygen, 5 in case of fluorine, and 6 in case of neon. So the configuration is NS2. In all these elements there are 2 electron in S. So, with some exception, in some cases, the NS electron can jump into the outer 2p orbital. That is another way for the expansion of their valency. But in general, the configuration of p block element is NS2, 2 electron in the S, and the in the p subshell, the electron ranging from 1 to 6. So the general electron configuration of the p block element is NS2 NP 1 to 6. That is about the general electron configuration. Next point is variable oxidation state. Variable oxidation state means they can show more than one type of oxidation state. So means all these p block element don't have the same oxidation state. Like in case of the S block element, it means group 1 element all shows +1, and the group 2 all shows +2 oxidation state. Means there are only 2 type of oxidation state in case of the S block, that is the +1 and +2, but they show more than that in case of the p block elements. In case of boron, you can see take the configuration of the boron 1s2 2s2 2p1. The configuration of the carbon is 1s2 2s2 2p2. In case of the nitrogen, 1s2 2s2 2p3, means the number of electrons in the valence shell are not the same one, like that of the S block element, where the group 1, in all the group 1 element, the number of electron is 1. In all the group 2 element, the number of electron in their valence shell are 2. But here, the number of electron moving from left to right, they do not remain same in their valence shell. In the valence shell of the boron, there are 3 electrons. In case of carbon, there are 4 electrons. In case of nitrogen, there are 5 electrons. With the difference that what is the number of unpaired electron in the paired electrons. In case of oxygen, there are 6 electron in their valence shell. Fluorine, there are the 5 electron in their valence shell. In the neon, there are 6 electron in their valence shell. So they have the tendency to show the variable oxidation state in their different type of compound. When you will see the compound related to boron or the carbon, you can calculate the oxidation state. So they can show the different variable state, different oxidation state. Different oxidation state shown means variable oxidation state due to the presence of different number of electron in their valence shell. So they have the tendency to show the variable oxidation state. Next, they are electronegative in nature. As you have already seen, in case of the S block element, they are the electropositive in nature. I already told you, okay, all element except group number 18, all are reactive in nature. All are reactive in nature. Means they want to get stabilized. They want to achieve the group 18 like configuration. To achieve that group 18 like configuration, they can lose the electron, they can gain the electron, they can share the electrons, they can do any one of the tasks. So these p block element, they have generally the tendency to gain the electron. So after gaining electron, they acquire the negative charge. So they are electronegative in nature. So the p block elements, they are electronegative in nature due to their accepting electron nature. So they are electronegative in nature, but they all elements are not the electronegative one. Means there is something variability in all the p block elements, because some elements are present at the top of the p block, means in the second period, some other in the third, fourth, fifth, and so on steps. In that way, they are present in the different period. Means their size will be different. We will discuss about the size later on. So means on moving down the group, you have already seen that the number of shell increases. So number of shell increase means the distance between the nucleus and valence shell electron changes. So the attraction changes. So the tendency to lose the electron also changes. Means that electronegative nature. Electronegative means non-metallic nature. The elements which have the tendency to take the electron, they are non-metals, and that elements which have the tendency to lose the electron, they have the metallic nature. So the p block elements, they contains the mixture of these elements. The most of the elements, these are the electronegative in nature. So we are saying here they are electronegative in nature. Generally, they are electronegative in nature because most of the p block elements are electronegative in nature. Some other are metal halide, means their nature is between electronegative and the electropositive, means their nature is between metal and the non-metal. And there are some elements which are at the bottom of these p block groups. They have something metallic nature also, but most of the elements, they are electronegative in nature. So we are generally saying here they are generally electronegative in nature. So that's the way to talk here, like that. So in case of the boron, the configuration is 1s2 2s2 2p1. Carbon 1s2 2s2 2p2, means on the basis of their configuration we can see how many electrons they will take from the other atom. In case of the fluorine 1s2 2s2 2p5, you can see here the configuration of the fluorine 2 to 4 5 9. Fluorine, that's the configuration, that's the diagram of the fluorine 1s2 2s2 and 2p5. Means the fluorine has the tendency to accept one more electron, and after accepting that one more electron, they becomes like that of the neon, because fluorine atomic number 9 plus 1 electron, that is 10 atomic number of neon, means group 18 element. So they have the tendency to take the electron. Like oxygen 1s2 2s2 2p4, means it can accept two more electron, and after accepting two electron, it becomes like that of the neon. So they are electronegative in nature. Means the element which have the tendency to take electron from another atom, that their electronegative nature, that's their electronegative nature, and they acquire the negative charge after gaining electron. So they are electronegative in nature. Neon is the exception here, means they have the fulfilled, neon has the fulfilled electron configuration. They cannot lose electron, they cannot gain electron. Means all other element like oxygen, fluorine, they want to achieve the neon-like configuration after accepting electron. So the number of electron which can be gained by these elements, oxygen and fluorine, that depend upon their electron configuration. As you can see, the fluorine can accept only one electron because there is the tendency to take one electron, because there is space only for one electron. So after acquiring one electron, so it becomes group 18 like configuration. So it is most electronegative element in the periodic table. The most electron negative element in the periodic table is fluorine, because after getting one electron, it becomes stabilized like the group number 18 elements. The second most electronegative element is the oxygen one. Oxygen, because after taking two electron, it becomes like that of the group 18 element. So means p block element, they are electronegative in nature. They have high ionization energy. Means as we already discussing here, that they are the electronegative nature. They have the tendency to take the electron. Means as they have the tendency to take the electron, means they reversibly we can say that, reciprocally we can say that they have no tendency to lose the electron. So means how can they lose the electron? For losing electron, for removal of the electron from their valence shell, for the removal of the electron from the valence shell of fluorine or the oxygen, very large amount of energy is required. So we can say here they have the high ionization energy. Means their valence shell electron cannot be lost easily, because they have more tendency to gain the electron than to lose the electron. So they are electronegative in nature. Due to their electronegative nature, they have more tendency to take the electron, and they can not lose the electron. So they have very high ionization energy. They can form both ionic and covalent compound. As we already discussed, the upper elements, like the second period element, the third period element, they are non-metallic in nature. They have more tendency to take the electron, means they form the ionic compound. Other element which have less tendency to lose the electron, means their nature is in between them, so they can form the covalent compound. Means many compound form the ionic compound, some other compound which also form the covalent bond, that depend upon their nature. Means the element like of fluorine, they have the more tendency to gain the electron, means they can form the ionic compound. Like that in case of the boron, you can see they generally form the covalent compound, because for getting the configuration like that of the group 18, because their atomic number is 5, they have to take 5 more electrons. So that is not easy to take the 5 electron, to gain the 5 electrons. In spite of that, Okay, the one of the 2s electron will jump into the 2p. There will be the 3 unpaired electrons. So by sharing, by mutual sharing, they can form the covalent bond. So on the basis of electronic configuration, by drawing their electronic configuration, we can explain about the nature of the compound formed by these elements, whether these elements can form the covalent compound or they can form the ionic compound. They can lose the electron or they can share the electron. So all these can be explained on the basis of their electronic configuration. Means boron can form the covalent compound, while the fluorine can form the, for example, NaF. Sodium atomic number 11, they can lose one electron, becomes atomic number 10, like that of the neon. Fluorine atomic number 9, they can take that particular electron. Means NaF is the ionic compound. NaF is the ionic compound. In that way, we can explain. Similarly, NaCl, that is the ionic compound, we can explain on the basis of the nature of the element by seeing their electronic configuration. So the p block element can form both type of compound, the ionic compound as well as the covalent compound. They are the strong oxidizing agent, as we already explained during the explanation of the characteristic of the s block element. Okay, the s block element, they are reducing agent because they have the tendency to lose the electron. Similarly here, the p block element, by seeing the configuration of the p block element, as they can form both covalent, the ionic compound, the element which can form the ionic compound, the element which have the more tendency to gain the electron, because after gaining these electron, they can becomes like that of the group 18 element. They acquire the fulfilled stable configuration. So as they have the more tendency to gain the electrons, so they are oxidizing agent. Oxidizing agent are those substances which have the tendency to gain the electron and get stabilized in the aqueous solution. That is the complete definition of the oxidizing agent. Never write the incomplete definition of the oxidizing agent. If that definition is asked in your examination, you can't write like that, okay, the elements which have the tendency to gain the electron. No, write the complete definition. The elements which have the tendency to gain the electron and get stabilized in the aqueous solution called as the oxidizing agent. Write like that. So next characteristic of the p block element, they are the poor conductor of the heat and the electricity, with some exceptions, because we have already discussed some elements which are present at the top. They have the non-metallic nature. As we move down the group, the size become increased, tendency to lose the electron, something increases, so something metallic characterizes. So they are generally most of the p block elements, generally we can say they are the bad conductor of heat and electricity, with some exception. For example, you can see in group number 14, the carbon, they can show the property of allotropy. Allotropy means the tendency of an atom of element to exist in more than one form. That's the allotropy. And the allotropes of the carbon are, you can already listen about that. Carbon allotropes are the graphite, there is a diamond, there is the fullerene, C60 fullerene. Means that particular property shows that the diamond is an insulator, but the graphite is a good conductor. Similarly, in case of the phosphorus, in group number 15, you will see nitrogen, below nitrogen there is phosphorus, also show the property with that allotropic form. There's the red phosphorus, white phosphorus, black phosphorus. That is a good conductor. Means that the exception about that term, that is that the p block element are the bad conductor of the electricity. Almost p block element are the bad conductor of electricity, with some exception. That in exception here, the graphite is a good conductor, that is the allotrope of carbon. The red phosphorus is a good conductor, that is the allotrope of the phosphorus. So these are the exception here. They are hard because they cannot lose the electron easily. We cannot cut them easily. They are hard non-metals, because some exceptions are there. Some are metallic nature also. So they are the characteristic of the p block element. They are hard, they are non-metal, with some exceptions. Bromine is a non-metal liquid. They have high melting and the boiling point. These p block element have the high melting and the boiling point. That's the next characteristic. They form the acidic oxide. Means these p block element, when they react with the oxygen, they form the oxides. And these oxides, because these element are there, the central atom of these oxide will be the p block element. For example, boron oxide B2O3, aluminum oxide Al2O3. Means the central element is the p block element, and that central element has smaller size as compared to the s block element, because as we move from s block to p block, On moving left to right, we will see that the size decreases. We will discuss it in later on also in the next lectures. Why the size decreases on moving left to right, why the size increase on moving down the group. Generally, we have seen the configuration of these S and the P block element. We also see that on moving down the group, the number of shell increases. So clear picture in our mind that the size goes on increasing with number of shell increases. As clear picture in on moving left to right, that the number of shell remains same, but the atomic number, nuclear charge increases, so attraction increases, size decreases. So that is the simple picture, but we will also discuss in detail about the size in the next lectures. So these, due to the on moving left to right, means on moving from S to P block, means P block element has smaller size than the S block element. So due to their smaller size, they have the tendency, according to the Lewis acid, they have the tendency to take the electron pair from the outside species. So that nature to take electron pair from the outside species, that nature, according to the Lewis scientists, called the acidic nature. Because the Lewis scientists explain the definition of the acid and base like that: the element or the compound which have the tendency to take the electron pair from the outside, they are acid, and the element or the compound which have the tendency to donate the electron pair to the outside species, they are the base, according to the Arrhenius scientist. So according to the Arrhenius scientist, their oxides, they are acidic in nature. Their oxide are acidic in nature. So all the P block element we will discuss later on, their compound also, their oxides are acidic in nature. We can also compare their acidity, which is more acidic, like in group number 13, boron oxide or the aluminum oxide, as we are discussing here. On moving down, the group size increases. So which will take the electron pair easily from the outside, boron or the aluminum, the element which has smaller size. So the smaller size is of boron. So boron oxide, in the boron atom of the boron oxide, have more tendency to take the electron pair as compared to the aluminum, because aluminum has smaller, something larger size as compared to boron. So which is more acidic out of the oxide of the boron or the aluminum? Boron oxide are more acidic in nature. Similarly, if we discuss about boron, next carbon, boron oxide or the carbon oxide, means carbon dioxide, which is more acidic, means as we move from left to right, the size decreases. So as the size of the carbon is smaller than that of the boron, so the carbon has more tendency to take the electron pair from the outside species. So the carbon oxide is carbon dioxide, means oxides of carbon is more acidic as compared to the oxide of the boron. So that's the basic trend according to the definition of the Lewis one. We can explain all these things later on also during the discussion on the topic of the acidity or the basicity. So these all are the characteristic of the P block elements. So that's, thank you for listening, keeping patience. Thank you very much.